In this video, we present a simple yet effective method for 3D semantic segmentation using Gaussian splatting. 3D Gaussian splatting is a powerful method for representing 3D scenes with compact, parameterized Gaussian primitives. However, this representation itself has no inherent understanding of language, making it incapable of handling open vocabulary semantic queries on its own. To enable open vocabulary capability, Gaussian splatting augments each 3D Gaussian with a language embedding trained from clip features extracted from the input images. These embeddings allow rendering of both RGB images and their corresponding language feature maps. Using these trained language embeddings, Gaussian splatting can directly perform open vocabulary 3D semantic segmentation, enabling precise, text-driven scene understanding. For example, given a text query such as wavy noodles in bowl, it can segment the corresponding region across novel views. One of the key challenges in open vocabulary semantic segmentation is maintaining multi-view consistency of language features. The same object can exhibit varying appearances across different views, which leads to inconsistencies in the language features extracted by clip. As a result, after training, the language embeddings often have low Gaussian similarity with the input text query when segmenting in novel views. Our method addresses this challenge by enforcing multi-view consistency, enabling the embeddings to maintain high Gaussian similarity with the text query even in novel views. The distribution of Gaussian similarity between the text query and the rasterized language feature map varies widely. However, previous methods use a fixed threshold, which often produces inaccurate segmentation masks. Our idea is to make language features maintain multi-view consistency. To achieve this, we augment each 3D Gaussian with two additional attributes: a learnable language embedding and a learnable identity embedding. Both are optimized together during training through the differentiable Gaussian splatting process. The identity embedding is kept consistent for the same object across different views, while the language embedding is supervised by clip features. To further enforce multi-view consistency, we apply the identity-aware semantic consistency loss. For Gaussians with the same identity, this loss maximizes their Gaussian similarity, pulling their language embeddings closer in the latent space. For Gaussians with different identities, it minimizes their Gaussian similarity, pushing them apart. This alignment ensures that the same object maintains consistent language embeddings across all views. We introduce a simple outlier filtering scheme to compensate for the inaccuracy of coherent identity labels generated by a zero-shot tracker. We measure the cross-entropy between the rendered identity feature map and the coherent identity labels, and exclude regions with high discrepancies from loss computation. This improves the reliability of the identity information and allows the identity embeddings to maintain consistent values for the same object across different views as training progresses. This is our overall architecture. Each 3D Gaussian is augmented with learnable language and identity embeddings, optimized through Gaussian splatting. Coherent identity labels from a zero-shot tracker and clip feature maps supervise these embeddings. The identity-aware semantic consistency loss pulls embeddings of the same identity closer, and pushes different ones apart. While an outlier filtering scheme removes unreliable identity labels during training. We propose a progressive mask expanding scheme to accurately extract object boundaries. Starting from the segment with the highest Gaussian similarity to the text query, the mask expands to neighboring segments with similar values. This iterative process considers local relationships between segments, producing more precise boundaries without relying on a fixed threshold. Here, we compare our method with previous methods on the LERF mask benchmark. Our approach produces more accurate segmentation masks that are well aligned with the input text query and preserves fine object boundaries. On the 3D OVS benchmark, our method also outperforms previous methods, delivering accurate segmentation masks and maintaining precise boundaries across diverse scenes. Thank you for watching, and please visit our website for more information.